All right. Hello, everyone. Welcome to the fourth and final session of our Spring 2025 program for the Virtual Inter-University Symposium on Infrastructure Management. For those who are new to VISIM, it is a virtual symposium that is hosted by Professor Pablo Durango-Cohen here at Northwestern University. Today, Jose, Gustavo, and Pablo will be presenting their work. Each presentation should be about 20 minutes long, after which we'll take questions from the audience. People can speak their questions or send them using the chat feature. I'd like to point out that this meeting is being recorded and will be made available shortly afterwards. Thank you all for attending. Our first speaker today is Jose Gustavo Ramos. Jose Gustavo obtained his bachelor's and master's degrees from the Federal University of Technology in Brazil and is currently pursuing a doctorate at the University of Illinois, Urbana-Champaign. Jose Gustavo has worked as a lecturer at Brazilian universities, teaching courses and supervising research related to the area of transportation. His research interests are railway components and operation, with a special focus on the study of rail creep and track degradation. And with that, I would like to welcome Jose Gustavo and hand it off to him.
Thanks for the nice introduction. So can I share my screen?
Yes.
Are you guys seeing it?
Yes.
Okay. So good morning, everybody, or good afternoon, depending on where are you. As he mentioned, my name is Gustavo Ramos, and I'm being advised by Arthur Lima, Marcus Darsh, and Riley Edwards here at University of Illinois at Urbana-Champaign. And today my talk will be about impact of higher speed rail introduction on track degradation and exploratory analysis. So here's my outline. I will start with a brief introduction about railroad track, about higher speed rail, and track degradation, then the methods and our research questions, and then some are results and the conclusions and path forward. Okay? So starting with a very, very high level about the railroad track. So railroad track is made of several different components, as we can see here and as we can see here in this right-hand side. Do you guys can see my uh, arrow here where I'm pointing at? Just to be sure. Okay. So we have the rails, we have the cross ties or ties or sleepers, depending on where you are, and we have the ballast. So the rail is this pieces. I believe everybody know. Uh, we have the sleepers or ties, which are these elements, and we have the ballast, which is these rocks. Okay. And also we have the subgrade, which is the ground beneath all this structure. So among the primary functions of the railroad track, we have it has to support and distribute train loads, to guide the vehicles, to provide adhesion at wheel-rail interface, to provide a smooth running surface, and this one will be very important for us today, and also to facilitate drainage. Uh, just fact here, in North America, 90% of the tracks have timber cross ties, which is not this case, and followed by 6% of concrete ties. Our study today will be done on a railroad that uses concrete ties, okay? So just keep in mind that it's the minority of the uh, track length here in US. So about higher speed rail. So is it a typo? I should be high speed rail. No, it's higher speed rail, not high speed rail. So it is defined as intercity passenger rail services with speed that are higher than conventional rail, but they are not high enough to classify as high speed rail by international standards, let's say. Okay, so we have a lot of definitions and speed range from country to country, but here we will define it, we will use it as passenger rail service running at 80 to 150 miles per hour. Usually, they have some degree of shared infrastructure with freight trains, especially in US, where we have uh, mostly of the track dedicated to freight. Uh, it's easy to make some modifications, some improvements on track, and then run these higher speed trains, then create a totally new dedicated track. Okay. It provides better passenger rail service and shorter travel times. But as I mentioned, we need some infrastructure upgrades. So we need wider curves to allow for these speeds. Also, the turnouts have to have higher diverging speed. And all the components, ties, fastening system, and ballast have now to consider this both types of trains. Also, the signaling system will change. Some examples in USA, we have Brightline that goes from Miami to Orlando that runs up to 125 miles per hour, and Amtrak from Chicago to St. Louis and from Los Angeles to San Diego, which runs from 110 and 90 miles per hour respectively. So now talking about track degradation, which will be the main question on this presentation now. So track degradation is an inevitable outcome of repeated train loading cycles. And here we have a video, and we can see very clearly this vertical movement that we have whenever we have a wheel passing. So this cyclical loading will lead to deterioration, okay, of these fastening components, of the tie plates, the cross ties, and also the ballast, okay? So train speed and also train weight are two key factors when we talk about track degradation. When we talk about heavy freight trains, they impose high static and impact loads, contributing to ballast crushing and subgrade settlement. When we introduce higher speed passenger trains, they have higher dynamic forces, so a higher vibration rate or higher frequency, let's say, which can amplify this degradation if track conditions are suboptimal. So we have a lot of research trying to understand this, okay? But the degradation patterns from field data, real life data for mixed traffic are still unclear. Okay, so this leads to our two research questions. Does the introduction of higher speed rail on a track that before had only freight train influence track degradation rate? Does this degradation rate change after the introduction of higher speed rail, and how it changed? And does maximum allowable track speed influence these degradations? So our field of study, we got data from 35 miles of Class 6 track located in North America. We cannot disclose exactly where the location is. It carries 30 million gross tons MGT per year, which is 15 MGT per track. We have two main tracks, except for a bridge section where it's single track. And something interesting, something particular about this place is that the track segments vary in age. So we have some brand new track that was constructed to receive this higher speed rail for this upgrade, let's say. So in the past, it was only main track with some passing sidings and some few sections with double track. So we have this very recently constructed track and some places that have cross ties and fastenings of more than 50 years old, okay? So it's mostly ballast track with concrete ties, as we can see in the right-hand picture, and higher speed rail was introduced after decades of established freight service. Today, the current traffic share is 86% of the MGT being freight up to 60 miles per hour with 10 trains a day, and 14% of the tonnage is from the passenger, which run up to 110 miles per hour with 10 trains a day. So the parameter that we used to measure track degradation was the rail profile. And what is rail profile? So the definition is that it represents the vertical surface uniformity of each rail. And it's usually measured using the midpoint offset of a 62-foot chord. So we can imagine that rail profile is a measure of how wavy the track is. Okay, we can see here in the ideal world we would have a totally horizontal track without any deformation. Okay, but in real life it's something like this. But we are exaggerating a lot. Okay, it's not a roller coaster, but this will be the measure of the profile. Okay, if we have a 62 chord here, we take this measurement and this is the profile. And usually on the track inspections, they take this measurement for every foot, okay? So according with the class of your track, you have some thresholds for this, the maximum thresholds for these values, okay? So if you are a class 6, as is our case, you can have a maximum of 1 inch, okay? So with this, you can allow for this higher speed rails, okay? High speed train. As we have this measurement for every foot, usually people in literature use the standard deviation of this, and they can be either positive or negative. In this case, here we could have something positive. People use the standard deviation of profile as a proxy for track degradation. So here we can imagine that each of these colored lines are different inspection dates, okay? And imagine that here we have a lot of profile measurements. So we get these profile measurements, and for this research, we have 30 months of data and a lot of inspection runs. We define inspection window length as 1/10 of a mile. So we have this inspection window. And we applied the aggregation function, which in this case was a standard deviation. So we have a lot of measurements here. We got the standard deviation of these guys, and we got a single value that is the standard deviation for this section, okay? And then we did this for all our track miles and for all these dates, and then we could generate a trend line here using the time in the x-axis and the standard deviation of profile on the y-axis. And the slope of this trend line, this regression line, is the degradation rate in inches per year, okay? So here we can see real data, how it looks like, and here we can see the degradation slope, okay? We can see clearly that is degrading over time, okay? So each different color is an inspection run, and if each dot here is a standard deviation of profile. So we split data into before and after passenger train operation start, and we classified each of these values and these places, let's say, with the predominant track age, if it was mainly old or new track, on this 1/10 of a mile, the track number, if it was on the first or second track, the maximum allowable speed, if it was low, medium, and higher. And at this point, it's important to say that we used maximum allowable speed as a proxy of track quality and geometry. So if we have a higher speed allowed there, it means that we have a long tangent section. On the other hand, if we have a low speed allowed there, it means that we have a sharp curve, okay? And also if it was pre or post higher speed rail introduction. To be valid, these degradation cycles, we considered at least 5 months of data, at least 15 geometry runs, so 15 points, data points, at least 90% of data on the window. So we can see some gaps here. If we have less than 90%, this run was excluded, okay? And of course, degradation rates that were positive. It's possible to have some negative, but it would be meaning that the track was self-healing, which unfortunately is not the case. Okay, so it could be some measurement error. So we applied statistics. Our data was verified to be non-normally distributed. So we used the Box-Cox transformation, as we can see here. And then we applied the ANOVA type 3 for unbalanced design because we have different sample sizes. And we considered the 2 factors and 2 blocks. The first factor was maximum allowable speed with 3 levels. And this is for passenger, okay? Lower than 60, between 65 and 79, and from 90 to 110 miles per hour. Factor 2 was the presence higher speed rail condition, pre or post this passenger train introduction. And we used blocks as blocks the track numbers and the age, old and new. Okay, so these blocks are factors that might influence, but we are not so interested on them. So the model will take it into account. And also we evaluated the combinations between the main factors on a post test. So here we have our preliminary results when we have our overall mean as 0.02 inches per year of degradation and the median 0.0012 inches per year. If we compare with Ramos, which is not me, he assessed the degradation for a class 1 railroad in United States with 90 MGT, much more than us, and he found similar values. Okay, but here it had concrete and wooden cross ties, and mostly were timber cross ties. Okay, if we get the mean for just concrete ties, we have 0.03 inches per year, which is a higher value than ours, which can be explained by this MGT difference. Okay, Fellinger found 0.015 inches per year on an Austrian railroad, and Valle and Lourdes found for a Portuguese high-speed rail values from 0.017 to 0.43 inches per year. And something interesting is that they found higher degradation for lower speed sections of their track. So here we have our ANOVA table. We can see that the only factor that was found to influence degradation when we consider only the main factors was the maximum allowable speed. So the higher speed rail introduction was not significant. The track number was not significant. Track age was not significant. And also the interaction between speed and the condition. However, when we did our post test, we could find that these 2 guys, so after the introduction of higher speed train, we have that the places with lower speed and the places with higher speed are degrading differently. And we can clearly see that the places with lower speed are degrading faster. Okay. Also, we can find that the places with the higher speed are degrading differently before and after the introduction of higher speed rail. And it's really interesting that our data is showing that after the introduction of higher speed rail, the track is degrading slower for these sections. Okay, so how can we discuss that? Okay, so before the introduction of passenger train, we had similar degradation patterns regardless of the location. We can state that at that time although we had all these speed locations as a proxy of track geometry, we had in reality only freight trains operating, and the traffic speed was only between 40 to 60 miles per hour. So maybe this low amplitude was not enough to cause significant difference on degradation. Also, Ramos et al. Found no difference between tangent and curved track degradation on that same 90 MGT freight corridor, which can support this finding. Also, when we find about the curves here, super elevation on curves was likely optimized to this freight speed, so these traffic patterns of freight trains, and probably it was, as it was optimized for this specific traffic type, we didn't have so much difference between curves and tangents, okay? So, in the other hand, after the introduction of higher speed rail, the places with lower speed that we believe that are the places with more demanding geometry, let's say more challenging geometry, they started to degrade faster. Okay, it is possible that now that we have mixed traffic, actually, one of these train types, either passenger or freight, are applying unbalanced forces on the curves, especially when we think about the super elevations, and then it is leading to a faster degradation. And how can we add this passenger train now? And now it's degrading slower in a slower rate than before. What we can state here is that maybe because now we have tighter FRA thresholds for profile, as we saw, maybe the maintenance quality is better now. So now they are carrying out maintenance that are meant to list more, So maybe this is overcoming this additional dynamic effects of the passenger trains. And we have some information that some undercuts were performed on the site recently instead of a tamping. So this can help support this hypothesis. So some brief conclusions and path forward. From the ANOVA test, maximum allowable speed was the only main factor influencing track degradation. However, we saw that with our post tests that speed influence is different before and after higher speed rail introduction. Locations with more challenging geometry degrades faster now than locations that allows for higher speeds. And we hypothesize that maintenance actions now are more effective than they were before, okay? As path forwards, we want to increase our sample size to be have more powerful statistics. We can update the analysis for 1/10 of a mile instead of 1/10 of a mile post. We can also get more data for the current condition. We can investigate the influence of curvature instead of maximum allowable speed as a proxy. Also, we want to investigate the influence of environmental parameters, for example, accumulated rainfall. We know that environmental factors dominate at low tonnage, while MGT dominates at higher tonnage levels, the degradation rate. And also we know that the water presence can increase degradation rate of concrete ties. So maybe we had a lot more rain before, and so that's why we have this difference on the higher speed sections. Also, we want to map the maintenance states and types to confirm this hypothesis about the 90 to 110 miles per hour sections. Thank you for the attention. That's what I had for today, and I will be happy to answer any question. Hope I was good with the time.
Perfect time. Thank you.
I'll ask you a quick question. I mean, unless someone else in the audience has one, but basically, there was something I didn't understand quite well, like at the start, which is basically using the standard deviation as your condition measurement, and so I think that what you have is I think you said that these were, I don't remember. I think that these were 20-meter long sections, and then you're assessing in these 1/10 of a mile larger sections, and so you're considering, I think, the standard deviation in that set as metric, as your condition metric for that range. And so the question is this: it would seem that if you have high profile measurements across these like 20-meter segments, that basically, so that would reflect poor quality, and it could be that the standard deviation is low. And so that's something that I did not understand. And then when you are measuring deterioration, and just to be clear, the degradation is basically increase in this standard deviation. And so in some sense, it's basically you're modeling the conditional heteroscedasticity of basically the track segment.
Yeah, exactly. So I can share my screen again. I think to be. So as we can see here for our real data, maybe here will be better. When we get this measurement, we will have usually they get with lasers, so they will measure this, and then we'll go 32 foot for each of the sides, and we'll measure the height. Okay, so it's for our measurements we have something very wavy. Okay, so it's based for a standard. Oh, let me go down. It's based on an imaginary horizontal plane. It's usually aggregated over the zero, okay? And we have positive values and we have negative values. So we can think this standard deviation of profile as a absolute mean of these guys. You know what I mean? Usually they will be around this zero value. Okay. I don't know if it was clear.
Thank you for explaining.
Okay, did it answer?
Yes.
And yes,
Thank you.
here we are getting this for 1/10 of a mile, and then we have this value. We'll have this representative value, and then we have for the next one. We get for 1/10 of a mile because it's hard to map this exactly same position for all the different dates. It's a challenge. So we have some error. So it's good to use this. Okay. We have to use this aggregation function. Okay. But the main point I think is that it's very around the zero. So it will be kind of a absolute mean. And the signal pattern will be very similar for all the dates, but the amplitudes will be changing. That's why the standard deviation is increasing.
I see. Thank you.
I had a quick question. For the higher speed rail services to start, the tracks have to be improved to a certain level, right?
Yes, that's
Are there
true.
any examples where those improvements have been made, but the higher speed rail services haven't been started yet that you could study to see if those improvements have a significant difference impact compared to when the services actually
Yes,
start?
yes. On our geometry runs, we have the curvature measurement,
Mhm.
and we can clearly see some places that the degree of curve was reduced. So we can take a look on this. So when this exactly started and how much of data we have with only freight passing with this improved track. Yes,
Gotcha.
we can do that. But maybe we will not have so much time to be confident about these results.
Thank you so much. Are there any other questions? If not, I will introduce our second speaker. Thank you so much, Gustavo.
Thank you very much.
All right. Our second speaker today is Pablo Teixeira. Pablo is a third-year doctoral candidate in civil engineering here at Northwestern University, and he might be in the same room as I am currently. He holds a bachelor's degree in civil engineering from Loyola Marymount University and a master's degree in operations research from University of the Republic of Uruguay. His research is focused on the application of real options analysis to infrastructure contracts, and I'm very pleased to introduce Pablo, and I'm very excited to hear his talk. So Pablo, please take it away.
Thank you, Gal. I'm trying to share my screen. Can you see there?
Yes.
Okay. So thank you, Gal, for the introduction, and thank you everyone for being here. I'm gonna be presenting the research that we're doing with Pablo for my PhD at Northwestern, and it's about infrastructure contracts and concessions. So when the government makes a concession to a private operator for a highway infrastructure, we're gonna be looking at those contracts and trying to determine in what ways we can make them more efficient. In particular, when we consider demand uncertainty. So when we are not sure about how many people are gonna wanna be using the road. And we're going to draw some parallels between this and financial markets. So the way we model this demand uncertainty for these contracts is going to be the same way that we model uncertainty for future contracts on some financial instruments. For example, on stocks, when we write options on stocks, we're going to be doing the same thing here with these contracts. But let's begin with a simple model of a road for a concession. So we're not going to be talking about demand uncertainty yet. We're going to be looking at a static model first, and then later on we're going to figure out how to add uncertainty in demand to this model. So we have some parameters here, the length of the road, the free flow travel time, a value of time, which we're using the same value of time for all the users, construction costs, which we're assuming the construction costs are going to be linear on capacity. So there's no fixed cost, there's no maintenance cost either. And then the capacity of a single lane, which we can then decide, these are the variables, how many lanes we want to build. So the total capacity of the road, which is going to be a multiple of K, and the toll that we want to charge, which could be zero or could be something else. With those variables and parameters, we also need to figure out how to model demand and how to model congestion, because we're going to be working with peak hours. So we're going to assume there's going to be some congestion on the road. So the total travel time is not going to be the free flow travel time. We're going to have to add some additional time for a congested road. So let's look at the demand first. We're going to just assume a linear demand. So it's going to be determined by these two parameters, delta 0 and delta 1. If you can see here, the intersection with the y-axis is going to be given by this delta 0, which we call the reservation price. So it's the price at which there's going to be no more users on the road. Basically, no one is going to be willing to pay more than the reservation price to travel on the road. And then for congestion, we're just going to use the VPR function, which we have right here. So it takes into account the free flow travel time, this one right here, but it also adds some additional travel time if there is congestion, depending on N, which is the number of users that we have on the road at that time, and then the capacity, which is given by the number of lanes multiplied by the capacity of a single lane. So you can see here, we're adding this tau, which gives us the toll to the congestion cost, and that gives us the total price that the user sees on the road. So they have their, given their value of time, however long it takes for them to travel on the road, plus the toll gives the total cost. And then if we make the intersection of that with the demand curve, we can find an equilibrium that gives us the number of users that are going to be on the road during that peak hour that we're modeling for. So that's basically the model that we have, the static model. And now the question would be, how do we optimize the two variables that we have? So the toll and the number of lanes that we want to build. And the answer for that is going to depend on who's making the decision. So let's look at some different points of view, and then we're going to see how we handle that. So the first point of view that we're going to be looking at is the point of view of the users. And the users are going to want to maximize their user surplus, which is given by this equation right here. So let's look at the components of that. The first part is the user's benefit. So it's going to be this area in green right here under the demand curve for the given number of users that we have at equilibrium. And to that, we're going to subtract the generalized cost, which is given by not only the toll that every user pays, but also the congestion and travel time cost that also every user pays. So we multiply both of those by n. And with that, we subtract that, and we're left with this triangle right here, which is the user surplus. So the users, from their point of view, they're going to want to have the maximum amount of user surplus for this project. Then another point of view is the point of view of the private firm. If there is a private firm that is operating, building and operating this road, they're going to want to have the maximum possible profit, which is going to be given by the toll revenues on one hand, so the number of users multiplied by the toll that they pay. And to that, they're going to subtract the construction costs, so the costs to build the road, which are given by this factor gamma multiplied by the length of the road multiplied by the number of lanes, since we said that in our model, the costs are just linear on capacity and we don't have any maintenance costs or fixed costs or anything like that. And then another point of view that we have is the point of view of the government, which is not exactly the same as the users because they also take into account what happens to the private firm. So they see the overall picture. And so their objective function is going to be composed of the sum of these two objective functions that we saw, not only the users, but also the private firm. And if you see here, we have the toll revenues that they cancel out. Since they're a transfer between the users and the private firm, and the government is overseeing the whole picture, they're not going to care about that transfer. They're just going to care about the overall welfare. So we're going to be left with this equation. And so we had those 3 points of view, the users, the private firm, and the government. Since the users don't really have a say in the project other than through the government, we're just going to be considering two agents in our model, which are the government and the private firm, and they both have their own objective functions like we saw. And then finally, to complete this simple static model, we're going to look at some different entry regimes. So depending on who is building the road and who is operating it, these three that we have right here, we're going to assume that the government is the one who is in charge of building the road and operating it. So for example, if we have a first best situation, the government will be doing everything and they will optimize to have the maximum welfare. On a second best, we add some constraint to that. So for example, we could say that the tolls that they charge are zero because people are not willing to accept paying a toll to travel on a public road. So that would give us a second best scenario. And we can also add other constraints. For example, if we want the road to be self-financing, we could add a zero profit constraint and see what happens there. And then we're going to be looking at some other types of entry where there is a private firm which is in charge of building and operating the road. They're charging a toll to the users, and that's how they're making their money back, basically, their capital investment on the road. But the government can choose who to give that contract to, and they're going to do that through auctions that we're going to simulate in our model. So the winner can be determined through different mechanisms. For example, you can assign the winner to whoever gives you the highest bid, or to whoever asks for the lowest possible subsidy, whoever promises to build the largest capacity, whoever charges the minimum toll, or whoever gives you the highest patronage, so the highest number of users that they can optimize through capacity and toll. So the combination of that gives you the highest number of users for the demand curve that you have at the beginning of the project. So we're going to be looking at all these different entry regimes. And that kind of concludes the first part of the talk where I wanted to introduce this static model. So now we're going to move on to the second part where we're going to introduce some uncertainty on the demand. So if you remember, we had a linear demand and I didn't mention anything about uncertainty, but because these contracts are long and they usually take like 20 or 30 or 40 years, the concessions that the government gives to a private company, it's reasonable to assume that demand is going to change over time and it's going to evolve. So it could look something like this. We're going to assume that the demand curve is going to move either up or down. The intersection with the y-axis is going to change, but the lines are going to remain parallel. So that's just an assumption that we're going to make. And we could plot how, if you remember, the intersection with the y-axis is determined by this parameter delta zero. So we're going to plot how the delta zero, the reservation price, evolves over time. So here we have time on the x-axis and delta zero on the y-axis, and we're just looking at, for a 40-year contract duration, we're looking at how delta zero changes over time. It would be reasonable to expect for it to be something like this, where population increases or demand increases and delta zero grows over time. But it's probably not going to look like that. It's going to look something more like this, where sometimes it goes up and sometimes it goes down. And if we do this for many contracts, we could have something like this. So we are always starting with the same delta zero. We're assuming demand, for example, is right here. And then the path that it could take could be something like this or like that or any other path within this. So to model that, we're going to be using a geometric Brownian motion, which is described by this differential equation right here. So this has two components, which are a deterministic part and then a stochastic part. So the deterministic part of this equation that we're going to use to model the evolution of the demand is given by this drift parameter. And then the stochastic part is given by this volatility right here, multiplied by delta zero, multiplied by this right here, which is distributed normally. So the growth rate of the price is going to be distributed normally, which means that the price itself is going to follow a log normal distribution. And I want to point out right here that this is the same way that many people model the evolution of stock prices. So this is the parallel with the financials market that I mentioned at the beginning. The evolution of stock prices can be modeled through a geometric Brownian motion. And so the valuation of future contracts that you can write on a stock price can be done in a similar way to what we're going to be doing here for our infrastructure contracts, assuming the demand behaves in the same way or a similar way to what a stock would have, with some volatility and a drift parameter that gives us the expected growth. And we're going to be borrowing a technique that we have from financial mathematics, which is a binomial lattice, like this. So to be able to evaluate these contracts. So what this does is we're discretizing this continuous process into a series of time steps where we are starting right here with an initial price. So this could be a stock price or it could be our traffic demand, whatever the variable is. And we're going to assume it can either go up or down at every time step. So for example, if we're right here, we can either go up on the next time step or we can go down, and the same for every other. And at the end of the contract, we're gonna have a distribution of possible values from the given starting one. We're not gonna go into how we determine this probability. So P gives us the probability of going up and 1 minus P gives us the probability of going down. And then we also have these two factors right here, U and D, which give us the factor by which we multiply the previous price. So for example, if we have delta zero right here, the next step, if we go up, we would have U by delta zero. And if we go down, we have D by delta zero, and so on and so forth. So I just wanted to draw the comparison between this discrete process and the equation, the continuous process that we had. So I plotted, just to illustrate, I plotted these values at the end, right? So the probability that we have of reaching each of these values. And we can see here I plotted for a few time steps, then I increased the number of time steps, and then I increased it some more, and you can see how this tends to a log normal distribution, which is what I said about the stock price or the demand parameter, is that it follows a log normal distribution. So you can see that if we increase the number of time steps a lot, we would tend towards the continuous process. But this discrete process is going to allow us to do some calculations on these contracts. So now with that lattice in mind, we have some functions that we're going to have to evaluate at every node on the lattice, depending on who is in charge of making the decision. So it can be either the private company or it can be the government. Each one of these agents is going to have their own objectives, and therefore they're going to have their own things that they're trying to optimize for every time step. The private firm is going to try to optimize the revenue, which is given by N multiplied by tau. And the government is going to try to maximize the overall welfare of the project. If you can see here, the state at each of these nodes is given by V plus delta V. So this is giving us the number of lanes that we have at that point, plus delta V is telling us the number of additional lanes that we want to expand to at any point during the contract. And this index J is telling us where on the lattice we are. So if we have a lower J, it's telling us we are on a higher demand, and if we have a higher J, it's telling us we are maybe over here with a lower demand. So for each of these points, each of these nodes in the lattice, we're going to be making this, evaluating these functions. If you notice, we need to determine the number of users that we have at each of these points. So we're going to be doing that by solving this equilibrium that we presented at the beginning for the static model. So we're going to assume that at each node, the demand is static. So we can do that. We can solve this equilibrium. Or if we have flexible tolls, so we don't know exactly what the toll is, then we're going to have to solve an optimization problem constrained by this equilibrium, depending on who's in charge of making the decisions, whether it's the private firm or the government. And then finally, we have this value to go functions, which what we're going to be doing is to figure out the present value. We're going to start at the end of the contract and then go backwards. So we're going to be doing a backward induction. So we need, for each point on the lattice, we need to evaluate these functions that we presented. So this part right here. Then we're going to subtract to that the cost of expansion if we're choosing to expand. So this delta V right here could be 0 if we're not choosing to build additional lanes. We're going to apply a discount factor, which we're not going to get too much into that for the sake of time. But then what we have right here is the expected cost of the remaining process. So if you imagine at a certain node, we're going to be looking at the two nodes that are ahead of it, so in the future. But since we're going backwards, we already calculated on those nodes, and we're just going to calculate the expectation, which if you remember from the lattice, when I presented it, I said that we have these values P and 1 minus P, which gives us the probability of going either up or down. So that's going to allow us to calculate the expectation. And with that expectation, we can go all the way back to the beginning. So we're starting at the end and doing backward induction to the beginning of the contract. And we're going to have the present value at the beginning. Before that, we need some boundary conditions. So we're going to assume at the end of the contract, there's no additional revenues or any additional welfare. And then these are the answers. So we go all the way back to the first initial node, and we can calculate the profit for the private company or the welfare in the case of the government. And to finish the talk, I just want to present, so with this methodology as a simple numerical example, we have some parameters right here. We're not going to get too much into those. And we have different entry regimes, which I presented before. So we're going to be looking at these different types of auctions. But the important part here is that since we have this evolution of demand over time and this uncertainty, what we want to look at is the options that whoever is in charge of the project has. It could be either the government or the private firm. They can have, and we're considering the option to expand the road. Or they could also have the option to vary the tolls. So at any point in time, they could decide to increase or decrease the tolls according to what the demand looks like, depending on what type of contract they have. So if the contract that they have with the government is more rigid, then maybe they are not allowed to build additional capacity, or they're not allowed to change the tolls at any point. Or if they have a more flexible contract, they may have those options, and that may affect the revenue for the private firm, but also the overall welfare, which is what the government, in theory, would care about. So we're going to be looking at, and here are the results from this numerical example, what the efficiency of each of these contracts is, so the different types of auctions, and whether they have these expansion options on these flexible tolls or not. So the important part of this table is this percentage right here, which is giving us the percentage of the welfare attained through this entry regime of the first best. So the first best, which we have right here, it will be the government in charge of the project, and they have all the expansion options, and the flexible tolls is always going to be at 100% because we're comparing to this first best. We're gonna be looking at how the different, this here in blue are the different auctions, how they perform with regards to the first best. So you can see, for example, here we have the highest possible efficiency, which is given for this last two auctions that we have. For example, this one is the minimum toll for a set capacity. So the government sets a certain capacity. For example, let's say they say, in this case, they would build 2 lanes. So that's the auction is just for 2 lanes, and they give it to whomever promises the lowest possible toll. So we can see that this has no options for anything, right? The capacity is already set at the beginning, and the tolls are going to be set at the beginning. They're not going. The private firm is not going to be allowed to change those tolls later on, even if the demand is really low or if it's really high. They're not going to be able to take advantage of that. But this is going to give us the highest efficiency in this example that we had. So I show that we have this parameter here, which is the volatility, which we set at 7.5%. So let's look at what happens when we change that volatility. So if you have here this parameter sigma, we were around here for a 7.5%. When we increase or decrease the volatility, we can see that the efficiency, so here I'm plotting this column right here. This is for the government, the 3 benchmarks, the 4 benchmarks that we had, first best, second best, and then some other types of entry. You can see that the volatility really affects these efficiencies. Here I'm comparing the different bid auctions, and I'm comparing the other types of auctions. So you can see that the efficiency really goes down a lot when we have higher volatilities for most types of auctions, but in particular for this one, which is a bid auction with options, so expansion options and toll variability. When we have volatility, the efficiency actually goes up. So this is telling us that depending on how much volatility you have for your demand, then the type of auction that you may choose can change, right? So the one that's going to be the most efficient may not be the same as if you had a lower volatility, because the higher the uncertainty in that demand is, then the more value that these options are going to have. So for a private firm, they may be able to adapt easier to a changing demand if they have the option to expand capacity at any point during the contract, or if they have the option to change the tolls that they're charging at any point in the contract. And that may make overall the contract more efficient, even from the perspective of the government, not just from the private firm, which may be counterintuitive, right? So to give all these options to the private contractor, but in reality, it may actually increase the efficiency of the contract, and this is what we're finding here with this model, and be the main conclusion that we've reached so far. So with that, that's the end of the talk. I'll leave my email here if anyone has any questions, or if anyone has any questions now, I'm happy to take them. Thank you.
Thank you, Pablo. If anyone has any questions, please feel free to speak them or put them in the chat.
I'll ask you a question, Pablo. And so, what happens? I mean, what happens to the firm profits as the volatility increases? Because I think you are measuring efficiency with welfare.
Yeah, I don't have that plotted. Um, But that also depends on the type of auction that you have. So if the firm is able to adapt to that volatility, then their profits might actually go up as the volatility increases, which could also be counterintuitive. If you have a really high volatility, you may think that a firm will be more averse to taking on that risk. But if they have that flexibility to adapt to it, then they can also make a lot of money, right? If the demand suddenly goes up to a really high value, they could, and if they have the chance to take advantage of that, their profits might actually go up when they evaluate the contract.
Yeah, I think that's what is interesting is that so it seems that both welfare and profit increase, and so that is an interesting result.
Thank you.
Pablo, the total welfare used in this involves both the user welfare and the firm's profit, correct?
The firm's profit is not part of the welfare
Okay.
because the total revenues are not included. Since they're just a transfer between the users and the firm,
Mm,
the welfare from the government's point of view, they don't care about that money.
gotcha.
So from what would be the firm's profit, the only part that is included in the welfare is the capital cost.
Gotcha. Thank you. Right. Any other questions from the group? If not, I'd just like to thank both Gustavo and Pablo for the wonderful presentations and for everyone for joining today. This is our final session of the term, so thank you everyone who's been attending this semester quarter, and we will send out more information for the upcoming term in the near future. Thanks, everybody.
Thank you very much. You all have a good weekend.